Thank you. Thank you all for being here. It's been really nice to be at KGRC this week. So yeah, I'm going to talk about, the title of my talk is Chromatic Numbers of Finite Subgraphs. So I want to talk about a problem that I think is an interesting combination of finite combinatorics and set theory. I want to start just by giving some very basic definitions that I think everyone knows, but just to make sure we're speaking the same language and have the same definitions. So of course, we all know what a graph is. Graph is a pair G. It's a pair VE. V is a set of vertices, E is a set of edges. We just think of E as being a subset of the set of two element sets of V. Okay. Now, once we have a graph G, we can do all sorts of things with it. One of the things we can do is color its vertices. So function C with domain V, the vertex set of a graph, is a proper coloring of the graph G if whenever C of U equals C of V for two distinct vertices U and V, UV do not form an edge in the graph. Okay, so proper coloring is a partition of the vertices into independent sets in the graph. Okay. And a very important number associated with the graph is its chromatic number, which is the smallest possible size of the range of a proper coloring of the graph. The chromatic number of G, which we'll denote today as chi of G, is the least cardinal chi such that there is a proper coloring C from the vertices of the graph into a set of size chi. We'll think of it as the set chi itself. Okay.
I guess vertices are not connected to themselves, right?
Right, exactly. So yeah, our edges are connect to different vertices, and there's only one edge between each pair at most. Yes. Okay, good. So the chromatic number is a fundamental object of study in graph theory. We're going to be interested in chromatic numbers both of finite graphs, but also of infinite and uncountable graphs. And a common theme in sort of combinatorial set theory, the study of uncountable structures, is asking questions about compactness of these structures. And what this means is we want to know how much about the global properties of a structure can we learn by just looking at small substructures. Right? These questions make sense in all sorts of contexts, but one place in which they're especially interesting is in questions about chromatic numbers or other issues about graphs. So the first real theorem in this direction is due to Bruijn-Erd H. The Bruijn-Erd H compactness theorem. It essentially says that if you want to know whether or not a graph has finite chromatic number, then it suffices to look at its finite subgraphs. Okay. More particularly, it says the following: if G is a graph, K is some natural number, and every finite subgraph of G has chromatic number at most K, then G itself, the entire graph, has chromatic number at most K.
I thought this was a homework problem in math. first logic course.
It probably was.
Propositional logic, but they
Yes.
proved it actually constructing a space which is compact and using
Yes.
the compactness of that space.
Yes. So from a modern point of view, this is definitely not this is definitely not an easy exercise by modern standards, but it's a foundational theorem in the field as well. Interesting side remark, in general this theorem badly ceases to be true if you talk about, say, countable chromatic number instead of finite. There are a number of papers showing that in a lot of models of set theory, this compactness theorem fails if you replace k by, say, aleph 0 and finite by, say, size aleph 1 or something like that. Not at all. Instead, the topic is the following. An immediate consequence of this theorem is the following statement. So therefore, if G is a graph that has infinite chromatic number, then we can define an interesting, I'll call it f sub g. It's a function from the natural numbers. So natural numbers. And I'm going to define it by letting, for all k less than omega, fg of k to be the number of vertices in, or the least number of vertices in a subgraph of G with chromatic number k. Fg of k is the least number of vertices in a subgraph of G with chromatic number k. Okay, so by this theorem, this must in fact be a defined function, defined everywhere into the natural numbers.
Why can't you jump over some
Right, so you can take away vertices one by one, and that can, if you take away one vertex, that decreases the chromatic number by at most 1. Right. Interesting remark, but that sort of intermediate value theorem doesn't hold if you talk about infinite chromatic numbers. So it's consistent that there's a graph of chromatic number aleph 2 that has no subgraphs of chromatic number aleph 1. But for finite graphs, it's easy just by taking them away. Right. Okay, so this function, partly by that remark, is an increasing function, strictly increasing function. And sort of the vague motivating question behind this talk is, how fast can f sub g grow? Okay.
Fast as you want, just glue together finite graphs.
Exactly.
Number.
Yes. Well, yeah, so it's not quite that simple, but not much more complicated. Because you need, those finite subgraphs to not have smaller finite subgraphs with large chromatic number.
Oh.
Right, which you can do. But yeah, it's not hard by some results of Erdős. That if you just want G to have chromatic number, Fg grow as quickly as you want. Okay, so Erdős proves that for every function f from omega to omega, there is a graph G with chromatic number of G equal to the size of G equal to L of 0, and Fg growing faster than F. Okay.
I withdraw my remark. What I said was complete nonsense. It's not an easy thing.
It's not easy. It's not easy, but it's also not hard if you take some theorems of Erdős as known. Yeah, but you do form this graph by gluing together disjoint copies of finite graphs, right? And this led him to ask the question: what happens if you ask more? What if you asked that the chromatic number of G is uncountable? Can you still make Fg grow as quickly as you might like? Right. And there are reasons to think that uncountably chromatic graphs might behave differently in this respect than countably chromatic graphs.
If you take some elementary submodel, will it not help? I mean, some elementary if you intersect the graph with an elementary submodel, will it not have the same function?
Yeah, but why will it have uncountable chromatic number when you shrink it?
Oh, I see. No, so I'm sorry. You want to
Yeah.
have a graph, and
What?
one graph with only one point.
Oh, yeah.
Or, yeah, we want large chromatic number, exactly. Yeah. Yeah, so it's the chromatic number we care about, not the size of the graph.
Yes. Okay.
Yeah. So, yes. As I said, there are reasons to think that uncountably chromatic graphs might behave differently. I want to give one example of a way in which countably chromatic and uncountably chromatic graphs behave very differently. Okay. To state this, I need a quick definition. The girth of a graph G is the length of the shortest cycle in G, if there is a cycle in G, right? So a cycle is just a sequence of edges that sort of starts and ends in the same place and doesn't repeat any vertices in between, and has length at least 3, right? Easy exercise: if a graph has no cycles, then its chromatic number is 2. In fact, if a graph has no odd cycles, its chromatic number is 2.
Or 1.
Or 1, yeah, at most 2. So there were some questions in the early days of graph theory about whether you can get graphs with large chromatic number and high girth. And Erdős proved this is true. So I'm going to state the version of this result for countable chromatic graphs. So for every k, there is a graph G such that the chromatic number of G is L of 0, and the girth of G is at least k. Okay, and again, this is achieved by, he proved a finite version of this, and this can be achieved by gluing together disjoint copies of finite graphs with larger and larger chromatic number. Okay. On the other hand, a result that I think was very surprising at the time it was proved by Erdős and Hajnal says that if a graph G has uncountable chromatic number, then G contains cycles of every even length, at least 4. And it contains odd cycles from some point on, right? So all of a sudden, going just from L of 0 to L of 1 chromatic, there are certain subgraphs, very simple subgraphs, that must appear there that might not have appeared earlier, right? Yeah, and sort of one reason for the difference is that when we want to construct L of 1 chromatic graphs, it's no longer enough to paste together disjoint copies of finite graphs, because you obviously won't get above L of 0 that way. You have to do something more complicated. Okay, so there are other theorems of this flavor that suggested that it's at least conceivable that this question about how quickly FG can grow could have a different result in the uncountable case versus the countable case. Okay, so I want to review some of the results about the uncountable case.
Beyond R1 also?
Not really. There are a lot of things still open. There are a lot of questions about what graphs must appear and what must not. But basically, what this theorem says is that every finite bipartite graph must appear in every uncountably dramatic graph. And those are the only graphs that must appear as subgraphs.
Is it true that if you have a graph with chromatic number LF1, can you find another graph, arbitrary large chromatic number, but with the same finite subgraphs?
That's like a version of the Taylor conjecture, right? I think that's either false or open. Consistently false, I'm pretty sure.
Yeah. Okay.
I would have to look at the literature. Yeah. Okay. Good. So.
You say first order, you have this configuration, you don't have this configuration. Just write down those axioms. So if they're consistent, then they're arbitrarily large models.
But the chromatic number.
The chromatic number.
Well, the chromatic number you can't control.
Yeah. Okay, so in a paper of Erd H, Hajnal, and Szemeredi from '82.
Are you going to cite a paper that doesn't have English on the author?
Yes. One.
Yours.
Mine, okay, two. Okay, Erd H, Hajnal, and Szemeredi in '82 investigated questions of this form. They constructed examples of graphs for which FG grows quite quickly. These are variations on what are called the shift graph. What they proved is for every infinite cardinal kappa, there is a graph G. Let me say this. For every infinite cardinal kappa and a natural number n less than omega, there is a graph G such that the chromatic number of G is at least kappa, and Fg grows faster than the n times iterated exponential function. Okay. And these graphs G are the shift graphs that are sort of well known in study of infinite graphs. They had been studied by Erd H and Hajnal much earlier. It was already known that their chromatic number was large. So the content of this theorem is that the Fg for these shift graphs G grows faster than the nth iterated exponential. And this was sort of the best known concrete example that they could find. And I think this paper was the first place where the general question was asked. So is it true that for all f from omega to omega, there is a graph G such that chromatic number of G is uncountable and Fg grows fast. Okay. So this appeared in maybe a slightly different form in this paper. This question appears in many other places. Erd H liked it a lot and put it in his problem collections.
Was it a dollar amount?
Hmm?
A dollar amount?
There's not, unfortunately. Yeah. Okay. There's an eraser somewhere.
There.
Oh, yeah.
Okay, so the next progress that was made on this question was a result of Commonwealth and Chella. No worries. It was published in 2005. So they proved that this question consistently has a positive answer. So consistently, and they proved, moreover, that you can find such a G of size L(1). So consistently, for every F, there is G such that the chromatic number of G equals the size of G equals L(1), and Fg grows faster than F. So this was a forcing construction. They started in a model of diamond and did a finite support iteration of CCC forcings length L(1) to get this. Okay. Good. And after that, there was really nothing. CH is true in their model. Yeah. And the main result of this talk, which I proved earlier this year, is that the answer to the question is yes in ZFC, with small caveats. Okay, so in ZFC, for every F from omega to omega, there is G such that chromatic number of G equals L(1), and Fg grows faster than F. Okay, you'll notice I omitted saying anything about the cardinality of G here. That's because the best I can do right now in ZFC is to get a graph G such that the cardinality of G is 2 to the L(1). Okay, I'll maybe talk a little bit more about this at the end. It is still open whether this size can be reduced to either continuum or L(1) in ZFC. Okay, so for the rest of the talk, I want to sketch at least a fairly detailed sketch of the proof of this theorem. Before we really start, we need two sort of preliminary tools, combinatorial tools. The first of them finitary, and the second of them infinitary. So first I want to talk about an object called a disjoint type. Okay, so here's the definition. A disjoint in parentheses. I might omit the word disjoint later on, but all the types we're talking about today will be disjoint types. A disjoint type of length n is simply a function t from 2n to 2 such that the size of the preimage of 0 equals the size of the preimage of 1, which is of course n, right? So intuitively, this sort of tells you how two disjoint sets of ordinals of size n fit into one another. Right? So a little bit more formally, if A and B are both subsets of the ordinals of size n, and they're disjoint, then the type of A and B is the disjoint type T of length n, such that if we let A union B be written in increasing order as alpha 0 up to alpha 2n minus 1, then T of I is 0 if alpha I is in A, and 1 if alpha I is in B. Okay, so we're just recording the relative positions of the ordinals in A and B. Okay, good. So what do I want to say about disjoint types? There's a particular family of disjoint types that we're going to be particularly interested in. We will be types of the following form. If we have two natural numbers s and n, where they're both at least 1, and s is strictly less than n, then call it TNS. Okay, now instead of writing down the formal definition of the function, types can be thought of as finite sequences of zeros and ones, right? N zeros and n ones. TNS is going to look like the following. I'm going to start with S zeros. It's going to end with S ones. And in between are going to be n minus s copies of 0, 1. Okay, so for example, T31, 0, 0, 1, 0, 1, 1. This would be the type of sets A and B such that the smallest two elements of A are below the smallest element of B, which is below the largest element of A, which is below the other two elements of B, etc.
Is 0, 0, 0, 1?
Nope, S is 1, so we have 1, 0, and then 3 minus 1 copies of,
Thank you.
yeah. Okay, good. All right, what are we going to do with these types? We're going to form graphs using them, of course. Yeah. And these are graphs that have been considered. First considered by Erdős and Hajnal. They're sort of buried in one of their papers and maybe not as well known. Okay, so if alpha is an ordinal, and T is a type, disjoint type, of length n, we can form the graph G alpha T. by letting, so the set of vertices of G is going to be the collection of n element subsets of alpha. And then there will be an edge set, E alpha t, where a pair AB of n element subsets of alpha is an edge if and only if A and B are disjoint and the type of AB equals T, or to make it symmetric, the type of BA equals T. Yeah, exactly. Yeah. Okay. And when we form graphs using these types T and S, we get some very nice properties. These were stated and not proven in a paper of Erd and Hajnal. So let's suppose we have two natural numbers s and n, and let's just say we have a cardinal kappa is an infinite cardinal. Okay, we have two statements here. The first is that the graph G, whose domain will be kappa, kappa to the n, and the type graph using type T and S. This has chromatic number kappa. Okay. It has cardinality kappa, so this is the largest possible chromatic number you can have.
Still without proof?
This, well, so there's a paper of Erd and Rado where they basically consider the graph using just this type. And they prove that G kappa T31 has chromatic number kappa. And then here they say it's the same as that.
Doesn't look obvious to me.
It's not obvious. We will probably see an argument later in the talk that is very similar to the argument for this, so you might be able to recreate this argument. The second thing that was stated without proof, and as far as I know, has never appeared in proof, in print, is also not obvious. So I have, it is true, I do know a proof of it. Says the following: if n is at least 2s squared plus 1, then G kappa T and S has no odd cycles of length 2s plus 1 or shorter. Okay, so this is also non-obvious, and I think the reason that it's never appeared in print is that it's sort of a tedious proof. But let's look at the special case of T31 and show that G kappa T31 has no 3 cycles, no triangles. And I'll try to prove this just by drawing a picture. Okay, I'm going to represent 3-element subsets of ordinals as lots of lines like this. So this will be one vertex in our graph. What does it mean for it to be connected to another vertex? It means that the ordinals are in this arrangement. Okay. Now, what are the possibilities for a third vertex that can be connected to the second one? The first is it's higher than the second one, in which case it's going to be disjoint even from the first, so it cannot be connected. The other possibility is a little bit more delicate, but not much. The other possibility is this. The middle ordinal in this third vertex is below the top ordinal of the first vertex, so it cannot be above, connected from above to the first vertex. On the other hand, the top ordinal of the third is above the middle ordinal in the first, so it cannot be connected from below to the first. So there's no way to have a triangle in this graph. Okay. If you try to directly generalize this type of argument to the arbitrary case, it quickly becomes too hard to actually draw the picture. But it's not too difficult to actually prove this
For
theorem.
fixed S, it's just a case distinction, a large case distinction, right?
Yeah. Yeah. You basically think about, as you get further away from an original vertex in your graph, what are the relationships that still must hold between the ordinals of the first vertex and whatever appears later. And if you have more and more overlap in the ordinals, then you get a stronger and stronger influence. Yeah. Okay, so that's all I want to say about disjoint types for now. I want to now move on to talk about our second combinatorial tool, which is more set theoretic in nature.
This is essentially the only way we know how to construct triangles in graphs.
In ZFC, yeah.
This is the only single construction for graphs.
Of size and chromatic number.
Yeah, size and chromatic number.
Yeah.
And your graph would have no short out cycles?
You can fix a length beforehand and say that it has no. It'll obviously have all eventually large odd cycles. Because, yeah. Okay, so the other tool that we're going to need is club guessing.
F2 will tell you what the cycles are going to get. We have a specific function. F3 tells you when you become non-bipartite. So anything shorter than that, there are no cycles.
Okay, easy.
Yeah.
The theorem gives a function.
Exactly. The theorem tells you what the
So
cycles are.
when the cycles start.
F3 tells you what the cycles are.
Yeah. Okay. Club guessing. Let me define what a club guessing sequence is. So let's suppose kappa less than lambda are regular infinite cardinals. And suppose that S is a stationary subset of S kappa lambda. This is my notation for the set of ordinals below, the other way around. S is a stationary subset of S lambda kappa. These are the ordinals below lambda with cofinality kappa. This is stationary. Okay. A club guessing sequence on S is a sequence C alpha indexed by alpha in S, such that, first of all, each C alpha is club in alpha, and it won't hurt us to shrink the C alphas, so we might as well assume that our order type is exactly kappa. And secondly, the important bit, for every club D at the top in lambda, there is one, or probably there are stationarily many, alpha in S, such that C alpha is a subset of D. Okay, so stage alpha you sort of guessed inside of D. So a club dressing sequence is sort of like a form of diamond. And somewhat surprisingly, maybe, in a lot of instances, club dressing sequences provably exist in ZFC. Okay. So Shalah's name is still up there. Theorem due to Shalah, not from 05. Which says that as long as there is at least one cardinal in between kappa and lambda, there is always a club dressing sequence on S. So if kappa less than kappa plus less than lambda are regular, and S is a stationary subset of S lambda kappa, then there is a club dressing sequence on S. Okay. This is a very nice theorem. The proof is quite nice. It's one of those proofs of Shalah where you just start with an arbitrary guess at something that might be a club dressing sequence. If it doesn't work, you fix it and try again. And eventually you'll succeed. Good. So I want to prove, or at least state, two useful lemmas about club dressing sequences. The first of them will be quite obvious. So if C alpha, alpha in S, is a club dressing sequence, so S is a subset of S lambda kappa for some lambda kappa, and we partition S into fewer than lambda many pieces, then our sequence restricted to one of these pieces will still be a club dressing sequence. And there is eta less than mu, such that C alpha, should alpha is in S eta, is still a club dressing sequence. Okay, and let me just try to say the proof. If this were not the case, then for each eta, you'd be able to find a club that's not guessed by any of the C alpha for alpha in S eta. You have fewer than lambda many clubs in lambda. You can intersect all of them. And now that smaller club will not be guessed by any of the C alphas in any of the S etas, contradicting the fact that the original sequence was club dressing. Okay. The other lemma, which is a little bit more involved, and will directly connect these two tools we have, is the following. To state this lemma, I need a bit of notation. If A is a set of ordinals and I is less than the order type of A, then A of I is the ith element of A in increasing order. I'll just write it informally, the ith element of A in the natural ordinal ordering. Moreover, if capital I is a subset of the order type of A, then I'm going to write A square brackets I to be the set of A of little I, set I is in I. Okay. So with this notation, we can state our lemma. Try to get this right. So I'm going to state it in not the most general form possible, but one that will be sufficient for us. Suppose lambda greater than omega is regular. S lambda omega is stationary. So here I'm focusing on cofinality omega ordinals. C alpha in S is a club guessing sequence. And T is no. So these can consistently exist on S omega 1 omega, and we'll be interested when they do. These, yeah, if M is greater than omega 1, they definitely does, but in general it might not.
Diamond itself would be a club guessing.
Yeah, diamond implies club guessing, obviously, yeah. Right, and T is a type, let's say, of length n. Then there are alpha less than beta, both in S, such that the initial segments of C alpha and C beta of length n witness this type. Such that C alpha n's, this is the first n elements of C alpha, is disjoint from C beta. And the type is T. Okay. So I'm going to sketch a proof of this. As we'll see, something much stronger is actually true. This is what we need.
You can almost get this without club guessing, right? I mean, for some, you'll have some small error. What can I say? There's going to be K such that C alpha square bracket K plus n minus K.
So, I mean, yeah,
Beta.
you can get this without club guessing, but
Not from the
we're going to need something actually, you can get it from the beginning, but the thing is, in our eventual proof, we're going to need something stronger than this. We're going to sort of need the combination of these two lemmas, right?
Yeah, I imagine.
Yeah, so like a sequence that would witness this not from club guessing would no longer have that property if you partition its domain, right? That's the intricacy. So yeah, this lemma on its own is overkill by far, as we'll see.
You're saying that you can set the oscillation of the two letters.
Yes. Yeah.
And what I'm saying is that, well, you start from the start of the
Yeah. Yeah. But then you want that also to be true on one of the pieces of a partition of S, whenever you partition S.
Any station, any letter system, any stationary system.
Eventually, like you could be stupid because you could put 0 in every letter.
We can all have 0.
Yeah.
That's
But
what I'm saying. That the type is going to be realized on C alpha bracket n plus k minus k.
Yeah.
So it's going to be in the middle of the type is realized in the middle of the
Yeah.
letter.
Yeah, definitely.
You can't control k.
Right.
Right. Yeah. So yeah, from club guessing you get something much stronger, which we'll see in the proof of this lemma. Okay. So in the interest of notational simplicity, we're just going to prove this lemma for our favorite type T31, which contains all the ideas of the general proof. Okay, so remember what this was. This was 0, 0, 1, 0, 1, 1. Okay, so what we're going to do is we're going to start by building a continuous epsilon increasing chain MC for C less than, where are we, lambda, of elementary substructures of some large h theta epsilon with a well-ordering of h theta and let's say a predicate for the C sequence, the club dressing sequence C. Okay. And moreover, we want to be the case such that for each C, MC has size less than lambda, and MC intersect lambda is actually an ordinal. Okay. Now, the point is, by continuity, the set of all such MC intersect lambdas is a club in lambda. So we can apply club dressing. So let's call this point B star C. So B star C such that C less than lambda, which we'll call D, is club in lambda. So there is, let me retroactively change notation because I feel like I'll just confuse myself if I don't. We're going to call this gamma and delta. Okay, so we can find a delta in S such that C delta is contained in D. Right? So what we get here is that every element of C delta is MC intersected with lambda for some MC in our sequence. Okay, and we're going to look at only those MCs of that form. Right? So for each I less than omega, remember C delta is an omega sequence. Let Ci be such that the ith element of C delta is M Ci intersected with lambda. And let's call this ordinal beta I. Okay, and let's rename this model Ni. Okay, so now we have an omega sequence of models, Ni for I less than omega, and the intersection of Ni with lambda is the ith element of C delta. Okay, now what do we have? The following statement is true in H theta. For each eta less than beta 2, the third element of C delta, there is some alpha 2 greater than eta such that there is gamma in S such that the first three elements of C gamma are beta 1 or beta 0, beta 1, alpha 2. Okay, this is a trivial statement because beta 2 and delta witness the truth of this. Okay, but my reason for writing this is that now this is a sentence only using parameters in N2. So it's true in N2. It's true for every eta less than beta 2, which is the supremum of N2 intersections with lambda. So in fact, N2 satisfies the following statement, where for shorthand, I'm going to let the notation exists.
This trivial sentence. You said.
You lost eta. Each eta what?
For every eta, there is an alpha 2 greater than eta, such that there is some gamma in S, such that the first three elements of C gamma are beta 0, beta 1, and alpha 2.
You said a witness for what?
A witness for alpha 2 is beta 2, and in that case, gamma will be delta.
And witness there is alpha 2, and gamma will be?
In S. Just in S. Anything in S.
Are the beta i's the same as beta I stars?
No.
Notice change.
Beta I is beta star Ci. Yeah.
This is the C gamma of 3. The first three elements of
Yes.
C gamma
Yes.
are
These are the first two elements of C delta,
yes.
right? And so if we let this alpha 2 be exactly beta 2,
Yes.
it's bigger than eta, and there is gamma, namely delta, such that C delta of 3 is,
Delta. Oh, delta is just for the guessing thing.
Yeah,
Yes.
yeah.
Yes, okay. Yes.
okay, good. So for reason notation, we're going to let this exists infinitely many alpha stand for there are unboundedly many alpha less than lambda, such that. Okay. So now if we look in N2, we have the following statement. There are unboundedly many alpha 2, such that there is gamma in S, such that C equals beta 0, beta 1, alpha 2. Okay. All right, but N2 is elementary, so this statement is actually true. Okay. Now we're going to play the same game one level down at N1. So for every eta less than beta 1, there is alpha 1 greater than eta, such that there are unboundedly many alpha 2, such that there is gamma, such that C gamma of 3 is beta 0, alpha 1, alpha 2. Okay, the witness here is beta 1 because of this. All right. If we keep playing this game down, so N1, let me just write this. N1 satisfies there are unboundedly many alpha 1, such that there are unboundedly many alpha 2, such that there's gamma in S. C gamma of 3 is beta 0, alpha 1, alpha 2. After one more iteration of this, we get down to N0 satisfies there are unboundedly many alpha 0, such that there are unboundedly many alpha 1, such that there are unboundedly many alpha 2, such that there's gamma in S, such that C gamma of 3 is alpha 0, alpha 1, alpha 2. So we've worked all the way down, and now we're going to work all the way back up, starting from the bottom. So we want some gamma such that the first three ordinals of C gamma are in this configuration with the first three ordinals of C delta. So we're going to apply this sentence, and then it's or the first two quantifiers in this sentence inside n0. It's beta 0. And then the last one inside beta 1.
But inside n0, why do you need anything to be unbounded?
Because you need to get above the first one you choose.
Oh, okay, so for the first one you don't need unbounded.
Right, exactly.
One and then the unbounded.
Right. So work in n0, find alpha 0 less than alpha 1, such that there are unboundedly many alpha 2 and gamma in S, such that C gamma 3 is, let me call these star, alpha 0 star, alpha 1 star, alpha 2. Okay. This is true in n0, so by elementary it's true, so it's true in n1. So now we can apply this sentence inside n1. To find alpha 2 star. Now we need it to be above beta 0. That's fine, because there are undoubtedly many of them. And we might as well go ahead and choose our gamma in n1 as well. Okay. And so we specifically chose our alphas in the right models so that the alpha 0, alpha 1, alpha 2 star are in the right configuration with respect to beta 0, beta 1, beta 2. Okay. And I hope it's clear that this can be done with any disjoint type. And in fact, something much stronger is true. You can realize any type with delta as the top point, right? So in fact, when we chose our delta, we knew nothing about the type that we were going to realize. So in fact, there's a single delta such that for every type T, there's a gamma less than delta in S, such that the initial segments of C gamma and C delta realize this type. Right. Okay, good. I have until 6, is that correct? Okay, so
If you want to split up, you can still pose a strict because underneath this thing needs to be club-guessing.
yes, exactly. So yeah, because we have the club-guessing sequence, we'll be able to use that lemma. Yeah.
So without club-guessing, sorry, I was wrong. Don't get this much. You can only set the oscillation. But the zeros and one describes when you switch from C gamma to C delta. So that's what you can do. At least that's
Yeah.
what I see.
Yep.
Not the exact 1, 1, 1.
Right. Right. Okay, good. So I think we have all the preliminaries we need now to start in on a sketch of the proof of the actual theorem.
And this is historically really interesting because Devil later used these oscillating types to prove his famous coloring result. These were skeletons were around in the 60s or around the
Yeah.
organization first.
Yeah. I knew that they were in this early paper of Erich Hajnal, but they're so hard to find. I had to ask Chromatic where they were in the paper. Okay, so yeah, we're going to prove our main theorem. Let's do it. remember what we have to do. We have to start with some function from natural numbers to natural numbers, and we have to construct a graph of uncountable chromatic number, g, such that f of g grows faster than f. Okay. We're going to do slightly worse than that, but in a way that will be clear that it's equivalent to what we actually want to show. So let me be more precise. We will construct a graph G such that chromatic number of G is aleph 1. As I said, the size of G is going to be 2 to the aleph 1. And for all k less than omega, and all subgraphs of G with at most f of k vertices, we'd like to say that this, let me give it a name, so perhaps H. We'd like to say that the chromatic number of H is less than k. And we can say that, but what's to be more convenient for our proof is going to be chromatic number of H is less than or equal to 2 to the k plus 1. Okay, so if we wanted it to actually be less than k, we can apply this statement to a function that grows much faster than f, and it'll be no problem. Right. Okay, but this is what's going to be most convenient for working with the actual graph. All right, now before I get into the actual construction of the graph, I'm going to outline some of its basic properties that will ensure that its finite subgraphs behave appropriately. Okay, so we will build G. The vertex set is going to be a set we'll call sigma, and the edge set E. Hopefully I can draw those distinctly. Satisfying, and as we build it, we're also going to build this auxiliary function from the edge set of G to omega. Okay, that will help us verify that the finite subgraphs behave as desired. So once we've done this, we're going to, for k less than omega, let ek be the preimage of k. So ek is all those edges that get labeled k by h. And gk would be the graph on the same vertex set, but only those edges labeled k, and g greater than or equal k, the same vertex set, and all edges labeled at least k. And we will have the following. Two important things. First of all, for each k less than omega, gk has no cycles, cycle-free graph. Okay. And second of all, and this method is similar in idea, if implemented differently, from the idea that Compactness and Hajnal used to ensure that their graph had finite subgraphs that behaved appropriately. G greater than or equal to k has no odd cycles of length f of k or shorter. Okay, so if you throw away the edges labeled with small numbers, you get rid of your short odd cycles in the graph. Okay, and these two things by themselves will guarantee that our finite subgraphs behave as we want them to. So once we've done this, now suppose H is a subgraph of G with at most f of k vertices. For j less than k, h sub k, which is the vertices of h together with the edges there that are labeled k, it's h intersect gk, I guess, has no cycles, bipartite, so it has a chromatic number at most 2. Hj. This is for j less than k. Chromatic number of hj is at most 2. And the rest of it, the rest of the edges are all in h greater than or equal to k. H greater than or equal to k has no odd cycles, because G greater than or equal to k has no odd cycles of length f of k or shorter, and H has at most f of k vertices, so there are no odd cycles there. So it's also bipartite and has chromatic number at most 2.
So say it again, why?
Yeah.
G has no short cycles.
Yeah, so G greater than or equal to k has no odd cycles of length f of k or shorter. This is a subgraph of G greater than or equal to k with f of k vertices. So if it had an odd cycle, then that would be a short odd cycle here. Okay, but what does this mean? So we have decomposed the edges of H into k plus 1 pieces. Each of those pieces has chromatic number at most 2. So we can properly color the whole graph by coloring each vertex with the k plus 1 sequence of zeros and ones given by the coloring each one. Coloring using 2 to the k plus 1 many colors. Okay. So the general fact, if you can decompose the edges of a graph G, then the chromatic number of G is at most the product of the chromatic numbers of all of those decomposed graphs. Okay, so we're left with constructing a graph that satisfies these two things, but also has chromatic number aleph 1. All right, so how are we going to do that? Let me first tell you what the vertex set is going to be. The vertex set sigma is, morally speaking, going to be all functions from ordinals less than aleph 2 to omega. But I want to focus not on all of aleph 2, but just on points in aleph 2 of countable cofinality. So let S be S omega 2 omega, points of countable cofinality below omega 2. As you might guess, we will later fix a club guessing sequence on this set. For beta in S, let sigma beta be the set of all functions f from S intersected with beta to omega, and let sigma be the union for beta in S of sigma beta. So sigma is the set of all functions from initial segments of S to omega. Okay, this will be our vertex set. I'll define sort of in stages how we define the edge set. One of our requirements, let me do one bit of notation first. If sigma is in sigma, let alpha sigma be the unique alpha in S, such that sigma is in sigma alpha. It's essentially the domain of sigma. Of sigma. So we will require in our construction of the graph that if there's an edge between sigma and tau, then one of them is an initial segment of the other. Okay, so sigma forms a natural tree by end extension. That tree has a comparability graph where two things have an edge if and only if they're comparable as initial segments. So what we're saying here is that our graph will be a subgraph of the comparability graph on this tree sigma. Okay, what else do I need to say about the edges? We will also require we're going to build these edges along with this function h. We're going to require that for all tau and sigma and all k less than omega, there is at most one sigma that's an initial segment of tau, such that there's an edge between sigma and tau, and h of this edge is k. Okay, so if you're at tau looking downwards, there's at most one thing down there that you're connected to and get colored k with under this function h. Okay. This will immediately ensure property 1 up here, that gk has no cycles, because if gk had a cycle, you should choose an element of that cycle with maximal domain. The two things on either side of it would be initial segments of it, two different initial segments of it, but they would get the same value with that maximal element under h.
Why would they get the same value?
Because they're in gk. Remember what gk was? Gk was those edges with pretending value k. Yeah. Okay. And the last two requirements are going to be probably the most important ones that will ensure our property 2 up there, and will also help us to add enough edges to make sure that we have large chromatic number. Okay, so finally, if sigma is an initial segment of tau, sigma tau is an edge, and the value of h on this edge is k, then two things. First of all, tau of alpha sigma must be equal to k. So when I've said that we're defining this function h along with the graph, I was sort of lying because it's given to us, right? As soon as we say an edge is there, the value of h on that edge is determined by the value of the longer function at the domain of the shorter.
What was the tau again? Oh, the tau is the tau.
Tau is yeah. So these are functions. Sigma is the initial segment of tau, so we can evaluate tau at the length of sigma. It's some natural number, and we require h of that edge to be that natural number. Okay. 2. Before I state 2, I need a little bit of notation. So for k less than omega, let s sub k be least. It's a natural number, such that 2sk plus 1 is at least f of k, and let nk be 2sk squared plus 1. The point is that that graph we define using the type t, nk, sk will not have any odd cycles of length fk or shorter. Right? Okay, now partition omega into adjacent intervals I0, I1, just we want each of these sk's to be at least 1, I0, I1, etc., with the size of ik equal to nk. So I0 is just the first n0 natural numbers, I1 is the next n1 natural numbers, and so on. Okay, so with this in hand, we can come over here and say, if sigma is an initial segment of tau, there's an edge, and they get numbered k under this function h, then we require that c alpha tau for all j less than or equal to k, c alpha sigma of ij is disjoint from c alpha tau of ij, and the type of these two sets is t nj sj.
You say they are disjoint.
They're disjoint, yeah.
Is this like a product graph? Or?
Not exactly. So the point of this is, so this is the point. The point is that the function that takes vertex sigma and sends it to the nk tuple c alpha sigma I nk induces a graph homomorphism from g greater than or equal to k to this type graph g omega 2 t nk sk. Right? Because if two things are connected here, it means they have are given color at least k by h, which means that the corresponding pieces of their ladders are in the right configuration to one another to be connected in this graph. Okay? Yeah. But this graph has no odd cycles of length fk or shorter. So this graph can't either. Because a short odd cycle here would be transformed to, well, a closed walk of odd length over here. But a closed walk can be decomposed into cycles, one of which must be odd.
The C's were the club guessing.
Yes. Yeah, exactly. Okay. So with these requirements in hand, it should be almost clear how to actually define this graph now. We just throw in as many edges as we can without violating these conditions. Don't even need to do it inductively. There's none of this is dependent on what you've done before, right? So for each tau and sigma, and each k less than omega, if possible, find alpha in S intersect alpha tau such that tau of alpha equals k, and C alpha tau, I'm not going to rewrite all this, but are in the right configuration to be added with h value of k.
So but there could be more than one, you just choose one.
Yep, exactly. And add tau restricted to S intersect alpha, tau to E for one such alpha. Okay, now it is clear, I hope, by what we've said, that this implies that the finite subgraphs behave as they should, right? Subgraph with at most f of k vertices will have chromatic number at most 2 to the k plus 1. What remains to show is that if we do this, the chromatic number of the resulting graph is aleph 1. Okay, so in the last 7 minutes, I'm going to try to do this. So as I'm erasing, let me just say that I hope it's not too hard to see that the chromatic number of this graph is at most aleph 1, because each tau is connected by an edge with at most omega many of its initial segments. And so you can recursively define a proper coloring by recursion on the domains of these vertices. Yeah. So so the coloring number of this is in fact omega 1. Okay, so we have to prove that it's uncountable. So suppose, for a contradiction, that we have a proper coloring C from sigma to omega, the proper coloring of G. Okay. I want to recursively define a function rho from S to omega by letting rho of alpha be C of rho restricted to S intersected with alpha. Okay, so at each stage of my construction of rho, I should sort this supposed proper coloring C, and that tells me what to add next. Okay. For each k, let Sk be the set of alpha in S, such that rho of alpha is k. This is a partition of S and counting the many pieces. So one of these Sk's still indexes a club guessing sequence. In fact, this sequence has a club guessing sequence. So fix k less than omega, such that C alpha for alpha in Sk is club guessing. In lemma that we proved about club guessing sequences and types, to find alpha less than beta in Sk such that for all j less than or equal to k, C alpha ij, let me just write this, the type of C alpha ij, C beta ij is T and J, Sj. So part of this is saying these are disjoint. The actual type that we're applying the lemma to is the concatenation of these finite types, T and J, Sj, for j less than or equal to k. Okay, that gives you a longer type. Okay, but now consider rho restricted to S intersected to beta. When we were deciding what to connect to it from below in our graph, when we asked about k, the answer was yes, there is some alpha less than beta, such that rho of alpha is k, and the c's are in the right configuration, right? Because this alpha is such a witness. So we actually did add something. It might not have been this alpha, but there's some alpha star less than beta, such that rho alpha star is k, and rho restricted to S intersect alpha star, comma, rho restricted to S intersect beta is an edge. But now look at what C assigns to each of these. C of rho restricted to S intersect alpha star. This is k, because rho of alpha star is k, and that's how we define rho. But this is also equal to rho of beta, because beta is in Sk. But again, by definition, this is C of rho restricted to S intersect beta. Right, so these two vertices are supposedly connected by an edge, but they're given the same color by C. Okay, so in my last 1 minute, I wanted to just make a couple remarks. One is, if diamond holds, then you have club guessing at aleph 1, and CH holds, so you can find such a graph of size aleph 1. In fact, you can do better. I won't give the definition, but for those of you who know, you can actually find a Hajnal mate graph witnessing this, if diamond holds. I want to end with just 2 questions that remain unsolved here. The first is, can you always find such a graph of size aleph 1 in ZFC? So in ZFC, is there always such a graph? Meaning, is it true that for every function from omega to omega, there's a whose function dominates f? And the other question that remains open, my graphs only have chromatic number aleph 1, and the technique seems limited to chromatic number aleph 1. Can you do better? So in ZFC, are there such graphs of arbitrarily high chromatic number?
Why do you say that this technique seems limited to
Because
what's so special about omega here?
it's 1 less than omega 1. In order to make the finite subgraphs behave correctly, I need to have some natural ordering of my vertices so that each vertex is connected to only count as many things below it. Right? I have this function h, and I required it to be 1-to-1 looking downwards. That immediately is going to ensure chromatic number aleph 0.
Why don't you just take functions into aleph 1?
Because the h was used to deal with finite subgraphs, and there are only aleph 0 many different types of finite subgraphs, right? Yeah, so it's it's unclear how a construction like this would work for a larger chromatic number. Okay, so I think that's all I wanted to say. Thank you for your attention.
Extremely clear lectures.
Oh, yes, of course.
So actually, I don't know. Are you sure that there are many graphs of such to be helpful and incomparable? Oh, uncommon chromatic number. Which realize this happening.
Oh, yeah, sure.
Yeah.
I mean, even in graphs of this shape, we made sort of arbitrary choices along the way.
Right.
Yeah. Yeah. Large family, I don't know, I don't know any that seem radically different from this type of construction, though. It would be
Non-isomorphic you get because you have somehow, but you have also non-pairwise intelligible.
Yeah, probably. I'd have to think more about the exact relationships
I can
there.
imagine that with the stationary sets of disjoint that you're building them on.
Yeah.
Like it.
Yeah, that would probably, yeah, definitely.
All right, well, thank you again.
Yeah.